Hi, all. I welcome you all for another podcast at SciTech Talks. This time we have an agri-robotics expert, Mr. Arun. He obtained his B.Tech in mechanical engineering from VIT University, Vellore, India, and MS in agricultural and biological systems engineering from University of Nebraska, Lincoln. He worked on machine learning based weed detection in UAV aerial imagery for his MS thesis. Currently, he's doing his PhD in computer science at University of Illinois, advised by Dr. Girish Chowdhary. His current work focuses on developing a vision and learning based navigation system for under canopy agricultural robots that can enable various applications like high throughput phenotyping, cover crop planting, etc. He has collaborated with research groups from diverse areas such as robot learning, approximate computing, human robot interaction as a part of his project. Uh, he also works closely with industry to deploy the outcomes of his research in large scale. Broadly, he is interested in using tools from robotics and machine learning to solve challenging problems in agriculture. Without wasting much time, let's talk and understand more about the research works, various research works that are taken up by Mr. Arun. And without wasting much time, let's go ahead and talk to Mr. Arun now. Good. Thank you so much for taking your time for this session today. Uh, Looking forward to know more of your experience in agri-robotics. So the first thing, actually, when I saw your profile, right, it was a transition from a mechanical engineer to somebody to converting into somebody who is doing research in computer science field, right? Could you please introduce yourself and then tell us more about what was your main motivation for getting into agri-robotics industry? And did you face any specific challenges for coming from a mechanical background and pursuing research in CS field? And so mainly because many of our listeners are like beginners who are getting started into research in the beginners who are getting started in the field of computer vision and image processing, deep learning, these areas. So if you can tell us maybe some perspective, give us some light on, did you face any challenges while you're applying for university applications? Because somebody from mechanical background, how did you motivate yourself, and how did you write your SOPs or everything? Maybe did you face any challenges in your US university application? If you can briefly cover these things in the first as a first question, it would be very useful for the listeners.
Sure. Yeah. First of all, thank you so much for the opportunity inviting me to talk here. My name is Arun Narenthiran. I'm a PhD student in computer science at the University of Illinois, Urbana-Champaign. So as you mentioned, I did my undergraduate degree in mechanical engineering. It was at VIT University, Vellore in India. So this transition was not really a conscious transition. The only motivation for all of this was I wanted to do something in the domain of agriculture. So I'm from the state of Tamil Nadu in India. I'm from a village. I grew up in a farm. My family still lives in a farm. So even before college, when I was thinking what I wanted to do, I had some inclination to do something in agriculture. But as you know, not you don't get a lot of support at home to pursue agriculture related things in India, because the kind of opportunities that we have, not much, right? So I chose engineering. I was good at math and stuff, so I liked engineering. I went to mechanical engineering. But this thought kept occurring to me. Okay, is there still something that I can do that is related to agriculture, engineering? So by the third year of my undergrad, I started looking at ag engineering related stuff that's happening in US and UK and Europe. It was kind of very fascinating to me. I had not seen, until then, it was more like I was going through the traditional mechanical engineering curriculum. I had not really thought about, I mean, you do think about how machines can be useful in agriculture, but since I was not a computer engineering student, I was not exposed to how much the tools in computer science and information technology can influence agriculture. So to see the kind of research, kind of things that was being done in agriculture in the Western world was fascinating to see. So I started thinking maybe this is a potential area to look at for grad school. So I started applying for master's in agricultural engineering. So I did not immediately shift to computer science. So the master's, I applied in agricultural engineering in several places. And then I went to University of Nebraska, Lincoln. I had a research assistantship and a fellowship to go, so I chose to go there. So during my master's in Nebraska is when my advisor kind of encouraged me to look more into machine learning, deep learning, and AI. Until then, in my undergrad, other than the one mandatory course that you take in computer science programming, I had not done anything which is computer science. So it was purely out of the interest to do something in agriculture that I kind of started pivoting little by little. So during my master's, it was in ag engineering, but the thesis was mainly on applying deep learning on imagery from drones, mostly like vision stuff, right? Like to detect weeds from drones. So I took courses and bunch of courses related to AI. So I got a minor in computer science. And then I applied to University of Illinois for PhD. It was still in agricultural engineering. So I work with Professor Girish Chowdhary. Our lab is like very interdisciplinary. We have students from various departments. So when I started at University of Illinois, it was still at the Agri-Engineering department. But I pivoted a little bit from doing just computer vision stuff in masters to kind of make it a little bit more robotics. I mean, it was still using drones and masters, but it was just in terms of analyzing the images, right? In this case, I started working on navigation, where it's a little bit different in terms of now you need things to real time. Like the output of your neural network has an influence on the decision. So I started getting more and more into robotics because I saw this as a way of connecting my undergrad in mechanical with what I learned in masters. Everything was kind of coming together, right? Like you see, you have this intelligence part, and then you have the embodiment in the form of the machine, and you are connecting everything together. And so I thought, like, I got more and more interested in exploring more into the AI and robotics part. So I thought being in the computer science department would give me more opportunities in terms of collaborating with a lot of exciting things that happens at Illinois. So I actually reapplied and then changed to the computer science department when I was at Illinois already. So in this case, my experience during my master's and also some initial work I did at Illinois kind of helped my case. So it's not a traditional way where I have some friends in my undergraduate university who did mechanical engineering undergrad like me, and then maybe they worked in some industry for some time related to AI, and then applied to CS directly. So that might be a more traditional route. In this case, it's more like it was driven by the motivation to do something in this domain, and then the tools kind of aligning through computer science.
Okay. Now I got you. Yeah. So I think that's very interesting journey how you have transitioned slowly. And then it makes sense, actually. Robotics is an amalgamation of several different things. And then unless and until we are aware of all these multiple components, it's quite difficult to make the robots to work and then for that specific desired applications. So you had experience of working with UAVs as well as ground-based robots, is it, here while you're doing
Yes.
PhD?
So UAVs, it's more like we were just using off-the-shelf UAVs and mainly just data collection, then followed by primarily working on the machine learning part. But
Okay.
in case of ground robots, the focus is primarily on navigation, which means I work mainly on the not just perception, but also the control part as well. So I wasn't working on control of the UAVs during masters.
Oh, okay. That's interesting. And I was I did my until May, actually. I did my postdoc at Lincoln Institute of Agri-Food Technology in University of Lincoln. Quite a few. I was from a computer vision background, but quite a few of my colleagues were from a robotics background, and they always used to work with these Thorwald robots mainly for strawberry picking and those kinds of an applications. They used to design the robotic arms and for picking based applications mainly. So since you have quite a bit of experience in both dealing with UAVs as well as ground-based robots, what do you think will be coming from a navigation kind of an experience in your research background? So what do you think will be the challenges associated with these UAVs or the ground-based robots specific to agricultural applications?
Are you asking from a navigation point of
Yeah,
view
yeah,
or like?
navigation point of view. Yeah. What are the different
Yes.
challenges that one can encounter while working for visual navigation in the agricultural specific based applications, basically?
Yeah, so I primarily work on the low level problem. In this case, it's like what we call the row following, or we can call it as similar to lane following, right? If you just look at that problem, uh, we can broadly classify based on the viewpoint of the robot into two types. One is the over the canopy and then under the canopy. When I say over the canopy, it's the drones or the tractors, which are kind of, the camera is more from above the plants. So you're kind of looking down, and so you're able to see multiple different, multiple rows of crops at the same time. In that case, to be able to do this row following task, you just need to be able to find these lines, right? And it's not very difficult. Like, in fact, I don't think you need machine learning to do it. This has been done by ag engineering people since last 25, 30 years. Like at Illinois, the vision-based autonomous navigation of tractor was demonstrated, I guess, even before 2000. So from the viewpoint of a top view for drones and tractors, I think it's kind of already a solved problem. John Deere tractors are probably already doing it. What we work on is, if we have these smaller robots that go under the plant canopy, especially in case of crops like corn or sorghum. So you're going under the plant canopy, but still the clearance is the same. You have only like 30 inches of gap to go through. So it's like you're navigating in tight space, and also in your given field of view, you only see this current lane. So the two lines of the crop rows are not like obviously visible due to various factors. There are like weeds, and there is like occlusion from the leaves of the corn itself. Because of these various sources of noise, the line is not obviously visible. Even if you try to use all these traditional CV techniques, it's difficult to segment the scene. The color of the plant is also changing continuously. It's difficult to find this line. So that's where we are trying to apply learning, right? Like how can you extract a useful representation from the scene using machine learning? That's basically my work. And then once you get this representation, you use it to do control. But broadly, your question on challenges in navigation, I would say, even in cases like the Thorwald robots, when you work in an orchard setting, this low-level problem is maybe not a problem at all in that case. It's similar to tractor or UAV. So there, the challenges come in the form of, maybe you have like multiple of these Thorwald robots, you want to coordinate them. How do you do task planning? So basically a lot of optimization like problems under constraints, I guess. Like there's probably constraints in the form of a given time within which you need to finish the task, like optimize for energy consumed by the robots. Also, if you have a human in the loop, then also safety comes into the picture. How do you have these systems? How can you ensure that they are operating safely when the human is still within the workspace? Things like that are pretty challenging. Yeah, but in case of UAVs, I would say the technology is very mature, unless we are trying to do some very high-speed stuff with UAVs. For the kind of spraying applications or like crop monitoring with UAVs, the technology is like very mature, that we already see a lot of commercial usage with these, not just here in, say, UK or US, even in smallholder farms in India. There's a lot of like people now offering services for spraying, right? Like with drones.
Yeah.
And they just mark the waypoints and the drones can do it. So for drones, mainly with single drone, already the technology is mature. Of course, again, if we make it like a swarm of robots, then with multiple robots, there might still be things to do in coordination and planning to do some exciting tasks.
Okay, okay. Thank you so much for sharing those. And yeah, I was in fact looking at your work on under the canopy stuff, right? Because some time back we wanted to get in touch with Professor Girish Chowdhary regarding the robot that they have designed. It's the Earth Sense, right? If I remember correctly.
EarthSense is the company that
Something.
manufactures the robot.
Yeah, yeah.
It's a spin-off from the university. Yeah.
Yeah, you did work with Earth Sense as well, if I remember correctly from your profile, correct?
Yeah, I interned at EarthSense last year. So my main goal was like I was focusing more from a research perspective in the lab, but I wanted to see when we try to deploy the systems in, like, say, larger scales from a commercial point of view, what are some challenges that we face. Because in the university setting, we try to do some very controlled experiments, of course, which is the very first step that's needed to get a good understanding of our various system components. But maybe the places in which we do these experiments are not a good representative sample of the various things that can go wrong, right? If you go to a farmer's field, especially like in the Midwestern US, you have these corn farms, which are like thousands of acres. There's so much things that can go wrong when you try to deploy in this scale. So that was my intention on, and I worked closely with Hudson on this regard.
Okay, okay. And to what extent these under the canopy robots are matured enough, or to what extent they are readily available at the moment?
So currently, for the phenotyping task, a lot of plant breeders have been using the EarthSense robots.
Okay.
But there are various issues. Or challenges rather. The challenges in the form of autonomy itself.
Okay.
So again, going back to the problem of row following. Because it's a machine learning based system, still we need to address this challenge of how do we deal with domain gap, right? Like we have trained the system on a finite set of data, but if you want it to operate in large scale in various different forms, we need to endow the capability of adaptability to these robots without requiring some human supervision or annotations, right? So that's still a challenge we are trying to tackle at UIUC here. Like how do we make these robots operate in this open world setting? Like as you go to different fields, there is going to be some slight domain gap, and we need to be able to adapt to it. But also there's another issue in the form of, say, a networking challenge. Currently, there's always a human kind of following the robot, even if the robot is in autonomous mode, because if the robot is making a mistake, like you just disengage, correct it, and put it back on track, right? But ideally, you don't want to follow it like all the time, like for thousands and or rather hundreds of acres even, right? But to be able to do that, we need to be able to communicate with this robot even from far. In case of these under canopy crops, the plant canopy is acts like a barrier almost in terms of signal interference, especially when the plant is green, the Wi-Fi signal, it gets absorbed. So it's hard to be able to transmit, say, video stream from the robot to the human to be able to teleoperate. So at UIUC, we've also been exploring some newer forms of technology for connectivity. We're working with experts in networking technology. They've been developing and testing infrastructure at the university farm here on this regard. So basically, how can we enable connectivity to teleoperate the robot so that in the event of failure, the human is able to come in and then recover the robot. So we need to address these multiple challenges to be able to scale this technology so it can become mature. But we are going there. So that's why currently this application of phenotyping can provide immediate value, since we are still talking about, I don't know, like maybe 10 to 100 acres of farm, research plots rather, right? But if you look at a farmer's case, especially we're talking about commodity crops, which are not like high value crops. So an average size of the farm is going to be like several hundred acres. So we can't scale up to that level until we have like very reliable autonomy with adaptation capability, as well as this networking issue like overcome. We need to overcome that.
Correct. I think, yeah, if you really have to deploy it at scale, I think multiple of them should work together. And for them, multiple of those robots to work together, a communication problem needs to be resolved. Yeah, it's always like an interlinked problem. I really understood. But it's very interesting to know that this, especially I wasn't aware that when the plants are green, Wi-Fi signal gets absorbed. So is there any strong technical reason behind that?
I mean, I don't know exactly the physics behind how this happens, but I guess mainly it's because of the water content in the plant that's causing the signal to be absorbed.
Okay.
Even just last month, I was doing some experiments where you see these huge variations in terms of latency. Like if you were trying to transmit something to the laptop using the robot's local Wi-Fi network, if I'm like following the robot right behind it within the crop row, the latency is reasonable. But if I just step out like to like couple of rows next to the current row, then you see this big jump. it's like it's just like maybe a couple of meters apart, but still the density of this canopy is like a big interference.
Okay. And even GPS also has a big issues, right? Even yeah,
Yeah,
the
so getting the uh, differential correction is the main issue. Like, so you can get an approximate GPS, which is up to like a meter or two accurate. But in this case, we are talking about a clearance of 30 inches. Like the whole space between two rows of crops is only like 75 centimeters. The robot takes up like half of the space. It's like 35 centimeters, I would say. So you
Mm.
only have another 30 to 35 centimeters to work with. But if the GPS error is like a meter or so, then that's not going to be reliable enough, right? So that's another challenge as well in case of drones and tractors. Even if we don't talk about vision-based systems, just pure GPS-based reference tracking will be like so good because there is differential correction available for the robots.
Okay. And I don't remember exactly if this robot was from your team or somebody else's. I've seen a few robots going under the canopy, and then they have a long stick on top of it, and which protrudes out of the canopy. And then I'm not sure if such kind of a design was made by your team or somebody else's. But if
We
it
don't
could
work with
partially
such
resolve
design.
the problem of this signaling part.
Yeah, so I have seen once another startup company in the Midwest area with a design like that.
Okay.
But in fact, before this project started, like 5, 6 years ago, the very first iteration of the design that was done by another group was pretty similar. It was basically like this one robot with this giant stick going out. But in case of corn, or even if you look at sorghum, like the plant is almost like 8 feet tall or more. So you need to have this giant pole sticking out, and then this pole is not going to be like very stable as well. And then because of this, the robot itself becomes huge than what our Terracentia is. So you have a bunch of issues like that. So it could work in certain cases, but it's not going to be like a general solution, right? We might be able to do some demos
Hmm.
and have
Correct.
some fancy videos, but is that what is going to get you a reliable system that scales up from start of planting to the end of harvest in all these row crops? At least I don't think so.
Yeah, correct. And I think before going to the next question, I have one small sub question actually. I was really curious about this under the canopy robots because I did did spend some almost like more than 15, 20 days for writing up one proposal here in UK. But
Mhm.
eventually I didn't proceed with that because of my job change and everything at that time. So the many research papers, if I see for under the canopy phenotyping, they falls under like so on they have these on uh, the corn or sorghum kind of plants, right?
Yeah.
So is there any specific reason the research is limited to those plants, or why isn't much research or the under the canopy phenotyping task has not much explored for the other crops? Is there any standard specific reason for that?
I think it's because of the structure of the plant itself.
Okay.
Because for any other crop, whether it's a horticulture crop or even in row crops, like other than corn, we grow quite a bit of soybean in the Midwest. Uh, uh, so in case of soybean, there are two challenges to use such an under canopy robot throughout the season. Like our robot is used quite a bit uh, for the first 40% of the growth stage. And then also when the soybean is very dry. But in the middle, what happens is at some point the canopy kind of closes completely. So there is not really like gap left anymore. It's pretty tight, especially some people also plant soybean in 15 inches. In that case, it's difficult to even use the robot to go inside because the robot itself takes up almost 15 inches.
Mhm.
And the other point of is in case of corn or sorghum, if you really want to image things from the top view, you really need to build something like you need to lift this tractor up with this huge uh, um, like suspension or something, right? Like whereas in case of soybean, most of the over the canopy systems can work pretty well throughout the season. If you just have because you just need the tire to go through the whole row instead of the robot itself, right? Like if it's covering multiple rows at the same time.
Mhm.
Um, and Uh, so I don't think it's mainly because of the structure of the plants. I would say that this whole under the canopy being like capturing, containing a lot more information is very specific to corn and sorghum.
Okay, it's the structure of the plants, maybe. Yeah, correct. Yeah, because I was exploring almost like more than 15, 20 days on this and thought of writing the proposal on designing such kind of robots. And that's when we got in touch with Professor Girish Chowdhary also at that time. And then somehow the communication didn't happen. We didn't go further because I had a job change and several other things at that time. And in fact,
The other
I
thing, okay,
attended the workshop hosted by Professor Girish Chowdhary at AAAI as well. And I was talking
uh-huh.
to, yeah, there were several people from your group, if I remember correctly, and then I
Yeah,
was talking to all of them and
I
understanding
see.
what are the different things that you guys have been trying on this stuff. Yeah.
Yeah. One more thing would be its structure of the plant kind of drives the what should be the structure of the robot as well, right? Because so even if you were interested in certain things which is at the base of the plant on anything other than corn or sorghum,
Hmm.
because you could still use a bigger robot or rather an over canopy robot, you just need a sensor that goes under the canopy, not really a whole robot that is small and going at a lesser height. You can just have another stick that goes out and an imaging sensor that's capturing something under. Um, that's
Thank
something I
you.
guess people do already in orchards quite a bit. Like you
Hmm.
just use the platform, but you just get the data from different viewpoints
Hmm.
uh, to capture different things.
Yeah. Yeah. So, but, fortunately, I had a chance of when I presented my work at AAAI, I visited Washington State University by Professor under the leadership of Professor Manoj Karki at that time, and then he gave me an opportunity to visit his lab. I had a chance to visit their orchards and everything, but they were not operating any robots at the time because it was an off season, and then they didn't show. I could not see any live demos, but it was very interesting on what are the different things that they've been doing on the grapevines and other apple orchards and other stuff as well. Good. Thank you so much for sharing these insights. And the next question I have is on modalities, actually. What are the
Mhm.
different kinds of modalities that you have worked on and image modality specifically, right? And how are they generally help you or aid for the visual navigation? And won't the robots become very expensive when when we use these kinds of robots as such?
Yeah, so at least in the navigation work, I primarily worked on cameras. I've collaborated on some other projects which were using LiDAR, but ever since my project started, you said the exact right thing. Our focus has always been to keep the cost of this platform low. So what is the cheapest a system that we can build that can be autonomous? So that's why I've always now focused on can we make it work with just the cheapest camera. So it's not just we're talking about cameras. Even among cameras, the depth cameras the RGBD cameras that we can get are still like at least $300 or more, right? Like depending on the brand. So instead we are looking at $30 cheap cameras. So even if you put like not just one but three of these, it's still less than $100 and significantly reduces cost compared to say in other works earlier than ours on under canopy navigation. You could see 2D LiDAR being used. Uh, Even 2D LiDAR costs like $1,500 to $2,000.
Yeah.
And we don't even have to talk about 3D LiDAR. That's like something well outside this range.
Hmm.
So our focus has always been with keeping in mind the cost of the robot. And in case of Dasentia, two factors that contribute to the cost earlier where 2D LiDAR was being used, which costed $1,500. And also from a compute point of view, it was using a computer that was costing $1,000 or more. So the choice of sensor, which is a camera, drove the cost significantly from $1,500 to $30. We also did this other work, which we can talk more in detail, but that was focused more on optimizing the neural network itself so that we can bring down the cost of compute. So if you could do inference of the neural network, but if the neural network needs lesser compute to do this inference, then you don't need the $1,000 computer. We were able to demonstrate that you could do it even with a $30 Raspberry Pi. So cost is something that we always take into consideration, and we don't use expensive sensors because of it.
Okay. I think that would be the most useful, especially for Indian agricultural kind of an environments, basically. And when I started my postdoc, actually, this reminds me of one of the conversation that I had with one of my friend. He's a full-time software engineer and a part-time farmer. He does farming
Okay.
during the weekends.
Yeah.
And then he actually apparently said to me that, Karthik, now that you're working in this, can you design me something with less than some 50,000 rupees?
Yeah.
Yeah, so he say that he found some very expensive solution for the weed detection and everything. And Indian farmers generally can't afford for such kind of a costly solutions. So can you design me something at a very low economical cost? I think that would be extremely useful. The research that you guys have been doing will be extremely useful, especially for farmers in the Indian kind of an environment where they can't afford for a bigger or the giant equipments in their farms. Good. So yeah, and also I've seen some, apart from agri-robotics, you seem to have some experience on neural network optimization. Can you please briefly talk about that as well? Yeah.
Yeah, that was an interesting paper. So that was a collaboration with another group. And again, the objective was motivated by this cost constraint that we had, right? So we were using $1,000 computer, but we were looking at, we were discussing, do we actually need this? And how can we get rid of it with a cheaper computer if possible? But we were running convolution-based networks, and it has to run real time for effective navigation. So the question we were asking is, now the network is, say, running at, let's say, 30 hertz, and it has certain amount of accuracy in predicting whatever things it's predicting. So do we need both of this? Does it have to run as fast as this for, say, an upper bound of the robot speed? And also, do we need this much accuracy? Because what we care about is eventually the closed loop performance, right? We are saying when the robot is going, it has to be in the middle of the row, and maybe we have certain preference. Like ideal world, of course, we don't want it to fail at all. But let's say we have an upper bound on in every 1 kilometer, we don't want it to fail more than twice. So given this high level application specific constraints, we worked on what is the maximum that we can prune this neural network, so that we still meet this high level constraint, but we reduce the compute requirement significantly. So we demonstrated that we can have the same navigation performance. So the exact same system that we had, but we were just able to do it with Raspberry Pi.
Okay, so that means more you wanted to design more of neural networks on operating on an edge platforms like Raspberry Pis.
Yes, I mean, any computer that is on the robot, we can classify it as edge platform, but you're right, more like compute constrained edge platforms like Raspberry Pis.
Yeah, I think that will be extremely useful in terms of power, and yeah, in terms of power requirement, I think that will be extremely useful. And so I was reading one of the paper posted on my LinkedIn feed by somebody, and then this was the paper accepted in NeurIPS. So I was just wondering, they were talking about pruning versus quantization. So did you experiment on those two parts as well in your research work?
Yeah, we did. So, of course, pruning and quantization, these are things that a lot of experts have looked at in different perspectives, right? So the key thing that our contribution was what is the metric with which you use to optimize? So typically you use only the some metrics defined on the output of the neural network itself, right? For example, in our case, our network is like taking in an image as input, and it is predicting the two states, which is the angle of the robot and then the position of the robot, let's say, in the crop row. So typically you would say you give a bound on what is the maximal error on heading and maximal error on position that you can have, and you just try to prune or quantize or whatever using that. But the way we posed the question was, maybe that's not the right way, or maybe we are being too conservative if we use that as the metric. The eventual metric that matters is the application level metric, which is how good I am in navigating So basically, if I have to navigate with maximum 2 failures in 1 kilometers, then what is the uh, lightest possible network that can do it, right? So that's why we did pruning with the goal being the application metric instead of the metric defined on the network itself. And we showed that you can be even more aggressive, like you can get even lighter networks than if you are operating with just network level metrics.
Okay. Good. Thank you so much. The last and most interesting question for our listeners mainly, right? So the thing is, if somebody wants to get into this field, what are the different kinds of research problems that somebody can take a look at? And if you have any useful inputs for the researchers who are getting into this field of agri-robotic vision, please share it across.
Sure, yeah. Mainly from an agriculture perspective, a major challenge when we use machine learning based systems is, of course, we try to get big data sets that are diverse enough to train like good models that can generalize. But we always need to account for this fact that how much ever big the data set is, when you work in real farms, there's going to be domain shift. There's going to be some kind of domain gap between your training data and what you encounter in the real world. So I would say if someone's interested specifically in this ag domain and if they are looking to work on computer vision, robotics related stuff, it's what we call this problem of open world machine learning or open world AI, which is how can our AI-based systems adapt either without requiring human labels, or even if it does, with very minimal labels, like areas like few shot learning, zero shot learning, meta learning, I would say are very interesting and would have a lot of impact in agriculture. When it comes to vision, we have now quite a bit of data sets that are available open source for agriculture compared to 5-6 years ago. So it'll be a good place to get started. You can take some of these data sets, but you could try to impose this additional constraint of you learn a good prior model, and from that working on things like how can this model adapt to say a new crop or very different lighting conditions, field conditions. Those are all some interesting problems to look at. Both from a crop monitoring perspective as well as robotic applications like navigation or manipulation, I would say. When it comes to robotics, which includes control in the loop, it's still challenging to make it to reduce the barrier of entry, mainly because if you look at robotics in general, simulators are like great way for anyone to get started, right? Like you don't have, not everyone has access to robots, and also infrastructure in terms of farms for us to go and do real experiments on real farms with robots. But unlike other applications in robotics, the challenging case is we don't have good simulators for our farms as well, for someone to work on control related issues or things in closed loop for agriculture. So that is something maybe as a community we should address, so that people from anywhere in the world, irrespective of the access that they have access to robots, could still do robotics research, can get started on robotics research. So on that regard, I would say computer vision is a good entry point to get started. And eventually we will have more and more maybe simulators and stuff for other ways to do robotics related research.
Okay. Thank you so much. I think that's a very useful point for the whole community to address the need for the robotic simulators, so that somebody can get started into this core robotics stuff more than vision. If somebody is interested, maybe having more of robotic simulators will be extremely useful. And yeah, computer vision, yeah, as you rightly said, the data sets are widely available now, and many people are putting a lot of efforts in making these data sets publicly available for computer vision research and everything. Yeah. And I think in the last 40 minutes, it was a very useful discussion, Arun. We started with your journey, and we discussed about the challenges associated with the over the canopy, under the canopy, UAVs, ground robots. We spoke about the sorghum, the challenges associated, spoke about the corn and the sorghum plants. and you spoke about the navigation. Especially the most interesting and the useful point is, can we do something really without an expensive camera? And I think that will be very, very useful kind of a research. And with the aim of reducing the cost of these cameras, and also we spoke about how AI can adapt without much of annotations. So can we really train the systems with lesser? And the neural network optimization part also is very much needed for making these low cost systems. I think thank you so much, Arun, for your time. I think it's a very useful discussion and will be very useful for the listeners, or the beginners. Mainly, as I said, the listeners who listen to these podcasts are the beginners, are the researchers who want to get started with their research in the field of computer vision, AI, and deep learning. And I think some of the useful advices or the inputs that you have given will be definitely useful to them. And thank you so much for joining us today.
My pleasure. Thank you so much for having me.
Yeah, good.